Welcome to this session. We will be introducing Deadlocks, a core concept in operating systems, which is under study and research since several decades. Let us identify a situation we would have encountered in day-to-day life. Imagine an ambulance serving a medical emergency getting stuck in such situations. Or imagine you getting caught while trying to reach the airport and you are running short of time. Such situations are generally termed as deadlock situations. More formally, a situation wherein two or more competing actions are waiting for the other to finish and thus neither ever does. Let me introduce an interesting example from theory of computations which is used to explain the deadlock situation called the dining philosopher's problem. The five philosophers sit at a circular table with a bowl of spaghetti in front of each philosopher. A fork is placed in between each pair of adjacent philosophers, and as such, each philosopher has one fork to his left and one fork to his right. As spaghetti is difficult to serve and eat with a single fork, it is assumed that a philosopher must eat with two forks. Each philosopher can only use the forks on his immediate left and immediate right. If all philosophers attempt to eat simultaneously, each trying to use both the forks, that would result in the situation wherein no one can get the second fork. In this case, philosopher 1 waits for the fork grabbed by philosopher 2, who is waiting for the fork of philosopher 3, and so forth, making a circular chain resulting in a deadlock situation. Let us now dwell into how deadlocks occur in a computer system. Typically, in a computer system, a process requires various resources for its execution, like processor, memory, and peripheral devices. Formally, a deadlock refers to a specific condition when two or more processes are waiting for each other to release a resource. Let us take an example to illustrate the concept how a deadlock will occur when two concurrent processes, say P1 and P2, are executing in a computer system. Let us consider two resources, say a printer and a plotter. P1 requests and holds the printer and at the same time P2 requests and holds the plotter. While holding the printer, process P1 requests for the plotter held by P2. But P2 has not completed the task with the plotter and hence is not able to release the plotter. While holding the plotter, process P2 requests for the printer held by P1, but P1 has not completed the task with the printer and is also waiting for the plotter held by P2 and hence not able to release the printer. Now we say that the processes P1 and P2 are in a state of deadlock, in which neither of them are able to complete their tasks with the resources held by them. Let us graphically represent this deadlock situation. Let us consider the progress of process P1 along x-axis and the progress of P2 along y-axis. Process P1 holds printer, say from time x1 to x3, and process P2 holds plotter, say from time y1 to y3. In this situation, the two processes are holding two different resources and hence there is no conflict. In other words, there is no deadlock. Now, if P1 needs the plotter from time, say x2 to x4, and at the same time P2 needs the printer from time, say y2 to y4, it results in conflict in using the resources. The region bounded by x2, x3 and y2, y3 is the segment where both processes A and B are simultaneously wanting to access the resource holding the other, and neither of them will be allocated. After getting the familiarity with the deadlocks, let us understand the various necessary conditions for a deadlock to occur. A deadlock will occur in a computer system if all the following conditions hold simultaneously. Mutual exclusion means that resource is assigned to only one process at a time. This means that a resource can be acquired by only one process at a time. Hold and wait condition leads to a situation wherein a process owns a resource and is claiming the other resource. No preemption condition leads to a situation where the granted resource to a process cannot be taken back by the operating system forcibly. Circular wait is a situation where each waiting process is waiting for the next process in the chain and none is able to get the resource. From this discussion, we have identified a situation called deadlocks and the various conditions leading to deadlocks. The resource usage plays a central role in deadlocks. Deadlocks are inevitable, so the operating system must be able to prevent the computer system from it. And even if it occurs, the operating system must be able to detect and recover from it.